Picture yourself 5,000 years ago, standing in the vast desert beneath a canopy of stars more brilliant than any night sky you've ever imagined. No city lights pollute the darkness. The Milky Way stretches overhead like a river of luminous dust, and thousands of stars pierce the black velvet dome above you. Most of these celestial lights follow predictable paths, rising and setting with clockwork precision. But there's something strange happening up there, something that doesn't quite fit the pattern. 5 bright stars refuse to stay in their assigned places. Night after night, these rebellious lights wander across the heavens in loops and spirals that seem to mock the orderly procession of their stellar companions. The ancient Babylonians called them wild sheep, because they strayed from the celestial flock. The Greeks named them planetes, wanderers, never suspecting that these mysterious lights were entire worlds, each one a complex sphere of rock, gas, or ice spinning through the cosmic void. Here's what's really happening when we see these wandering stars. We're witnessing the greatest family portrait ever assembled. Those 5 bright wanderers, IS, Mercury, Venus, Mars, Jupiter, and Saturn, are our planetary siblings, reflecting sunlight across the vast distances of space to reach our eyes. When ancient observers tracked their movements, they were unknowingly mapping the architecture of our solar system, recording the dance of worlds that has continued for billions of years. The ancient Babylonians possessed a patience that puts our modern instant gratification culture to shame. For over 1,000 years, priest astronomers climbed ziggurats in the pre-dawn darkness to observe and record the positions of these wandering lights. They etched their observations onto clay tablets using cuneiform script, creating humanity's first systematic astronomical records. These dedicated skywatchers had no telescopes, no computers, no understanding of gravity or planetary motion. They possessed only their eyes, their minds, and an insatiable curiosity about the cosmic ballet playing out above their heads. What they discovered would have seemed impossible to them if they could have understood its true meaning. The wandering star we call Mercury completes its celestial journey in just 88 days, racing around an unseen center point at incredible speed. Venus, brilliant and beautiful, follows a pattern so regular that it became the cosmic timepiece for multiple civilizations. Mars glows red in the night sky and occasionally appears to move backward against the stars, a phenomenon that would puzzle astronomers for thousands of years until Johannes Kepler finally solved the riddle of elliptical orbits. The 2 outer wanderers visible to the naked eye, Jupiter and Saturn, move with stately slowness across the star field. Jupiter takes nearly 12 years to complete its celestial circuit, while Saturn requires almost 30 years. To the ancients, these planets seemed eternal and unchanging, divine messengers carrying the will of the gods across the heavens. They had no way of knowing that Jupiter is actually a failed star, a gas giant so massive that it warps space around it, shepherding asteroids and comets with its immense gravitational influence. They couldn't imagine that Saturn possesses the most spectacular ring system in the solar system, billions of ice particles spinning in perfect formation around the planet's equator. The universe has a surprise for us when we consider what those ancient observers were actually seeing. Every photon of light that reached their eyes had traveled millions or even billions of kilometers through space, carrying information about distant worlds. When they saw Venus shining like a brilliant diamond in the evening sky, they were seeing sunlight reflected off clouds of sulfuric acid, surrounding a world where lead would melt and the atmospheric pressure could crush a human body in seconds. When they admired the steady red glow of Mars, they were seeing light bounced off iron oxide, IFR, rust, covering a planet where ancient rivers once flowed, and where the largest volcano in the solar system rises 21 kilometers above the surrounding plains. But here's perhaps the most remarkable thing about those ancient observations. They were witnessing gravitational choreography on a cosmic scale. The seemingly erratic movements of the planets actually follow precise mathematical laws. Each loop and spiral traces out the interaction between Earth's motion and the motion of the other worlds, creating geometric patterns of stunning complexity and beauty. The retrograde motion of Mars, those puzzling backward movements that confused ancient astronomers, occurs when Earth's faster orbit carries us past the red planet, creating the illusion that Mars is moving backward against the stellar background, much like a fast car overtaking a slower one on a highway. The Greeks elevated planetary observation from practical timekeeping to philosophical inquiry. They asked profound questions that we're still working to answer. What is the nature of these wandering lights? How do they move? What controls their celestial dance? Aristotle proposed that the planets were embedded in crystal spheres, perfect transparent shells that carried them around the Earth in eternal, uniform motion. This model seemed reasonable given the available evidence, but it contained a fatal flaw that would eventually bring down the entire Earth-centered view of the cosmos. The problem was precision. The more carefully astronomers observed planetary positions, the more complex their theoretical mechanisms had to become to match reality. By the time of Ptolemy in the 2nd century, the crystal sphere model had evolved into an impossibly complicated machine of wheels within wheels, with planets following circular paths called epicycles, while simultaneously orbiting Earth on larger structure, circular paths called deferents. The mathematics worked, after a fashion, but the physical picture had become absurdly complex. For 40 centuries, from the first Babylonian observations to the invention of the telescope, humans gazed upward at these celestial mysteries without understanding their true nature. They were looking at worlds, actual spheres of matter, with mountains, valleys, atmospheres, and perhaps even life. They were observing a gravitational symphony where each planet influences every other through invisible forces that operate across vast distances of space. They were witnessing the end result of cosmic evolution, the transformation of a primordial cloud of gas and dust into a complex system of worlds, each one unique, each one holding secrets about the fundamental processes that shape matter in the universe. The 5 naked-eye planets represent just the beginning of our solar system's story. Hidden beyond the reach of unaided human vision lie 3 more worlds. Uranus, spinning on its side like a cosmic bowling ball. Neptune, where winds rage at 2,100 kilometers per hour, despite receiving almost no energy from the distant sun. And tiny Pluto, dancing in gravitational resonance with Neptune at the edge of interplanetary space. Scattered throughout the system are more than 200 moons, millions of asteroids, billions of comets, and countless smaller objects, a vast collection of debris left over from the solar system's violent birth 4.5 billion years ago. When we look up at Venus hanging like a brilliant jewel in the twilight sky, we're seeing the same light that inspired poets, guided navigators, and puzzled philosophers throughout human history. But now we know the rest of the story. We know that Venus rotates backward, taking longer to spin once on its axis than to orbit the Sunday. We know that its surface temperature could melt lead, and that its atmospheric pressure would crush a submarine. We know that, somewhere in that hellish environment may lie clues to understanding Earth's climate and the delicate balance that makes our world habitable. The wandering stars that captivated ancient observers have revealed themselves to be entire worlds, each one a unique experiment in planetary evolution. They've shown us that our solar system is simultaneously more violent and more elegant than anyone imagined. They've demonstrated that the same physical laws that govern motion on Earth also control the movements of objects separated by hundreds of millions of kilometers of space. Most importantly, they've taught us that we live in a universe where matter organizes itself into structures of breathtaking complexity and beauty. Tonight, when you look up at the wandering stars, you're participating in a tradition that stretches back to the very beginning of human curiosity about the cosmos. Those ancient observers who climbed ziggurats and consulted star charts were asking the same fundamental questions we ask today. What's out there? How does it all work? What is our place in this vast cosmic arena? They may not have known they were looking at other worlds, but they were taking the first steps on a journey that would eventually carry human-made objects to every planet in the solar system and beyond, into the space between the stars themselves. The darkness no longer holds the same secrets it did 5,000 years ago. We've solved the mystery of the wandering stars, but in doing so, we've uncovered even greater mysteries, even more profound questions about the nature of worlds, the origin of life, and the possibility that somewhere out there, on one of those distant points of light, other curious beings might be looking back at us, wondering about the bright blue star that rises and sets in their alien sky. The story of the solar system begins with those 5 wandering lights that refuse to stay in their assigned places in the cosmic order. It's a story that transforms points of light into entire worlds, ancient observations into modern space missions, and human curiosity into the greatest adventure our species has ever undertaken. We are no longer passive observers of the cosmic dance. We have become participants, sending our emissaries to visit other worlds and preparing to follow them ourselves into the vast frontier that surrounds our small blue planet. The wandering stars have shown us that we live in a universe far stranger and more wonderful than our ancestors could have imagined. But they've also shown us that the human desire to explore, to understand, and to reach beyond our immediate surroundings is as old as astronomy itself. Those ancient observers who tracked planetary motions on clay tablets were our direct predecessors in the greatest adventure story ever told: the exploration of the solar system and our search for our place within it. 4,600,000,000 years ago, in a quiet spiral arm of the Milky Way galaxy, something extraordinary was about to happen. Picture a cloud of gas and dust so vast that light would take several years to cross from one side to the other. This stellar nursery contained all the raw materials needed to build worlds: hydrogen and helium left over from the Big Bang, and heavier elements like carbon, oxygen, silicon, and iron forged in the nuclear furnaces of massive stars that had lived, died, and exploded as supernovas billions of years before. Here's what's really happening in this cosmic construction zone. Gravity is about to perform the universe's greatest magic trick, transforming a diffuse cloud of particles into a family of worlds. But this transformation won't be gentle. The birth of our solar system will be a story of violence, collision, and catastrophic change that makes the most dramatic events in human history seem like minor disturbances by comparison. The process begins almost imperceptibly. Perhaps a nearby supernova sends shockwaves rippling through the interstellar medium, or maybe the gravitational influence of a passing star disturbs the delicate balance within the cloud. Whatever the trigger, density variations begin to appear in the gas and dust. These slight irregularities become the seeds of destruction and creation. Gravity amplifies tiny differences into cosmic drama. Where the cloud is slightly denser, matter begins to accumulate. As more material falls inward, the gravitational pull becomes stronger, attracting even more gas and dust. This runaway process transforms gentle attraction into inexorable collapse. The universe has a surprise for us in how quickly this happens. What begins as a barely perceptible condensation becomes a violent implosion over just a few 100,000 years, an eye blink in cosmic time. As the cloud contracts, it begins to spin faster, just like an ice skater pulling in her arms during a pirouette. This rotation flattens the collapsing material into a disk, with most of the mass concentrated at the center. The spinning disk becomes a cosmic furnace as gravitational energy converts into heat. Temperatures in the central region climb to millions of degrees, creating conditions so extreme that atomic nuclei begin to fuse together. The moment of ignition arrives with spectacular violence. Nuclear fusion begins in the dense core, and our sun is born in a flash of light that outshines nearby stars. But this newborn star is nothing like the stable, well-behaved sun we know today. The early Sun is a violent, temperamental object that blasts the surrounding disk with intense radiation and powerful stellar winds. These cosmic hurricanes strip away much of the remaining gas and dust, but enough material survives to begin the next phase of planetary construction. The leftover disk becomes a cosmic demolition derby where worlds are built through countless violent collisions. In the inner regions, where temperatures are hot enough to vaporize ice and drive away most gases, small particles of rock and metal begin to stick together through electrostatic forces. These microscopic collisions create larger and larger aggregations, from dust bunnies to pebbles to boulders to mountain-sized objects called planetesimals. Here's where the process becomes truly dramatic. As these planetesimals grow larger, their gravitational influence increases, allowing them to sweep up material more efficiently. The largest objects become gravitational bullies, cannibalizing their smaller neighbors in a feeding frenzy that lasts for tens of millions of years. Each collision releases enormous amounts of energy, heating the growing planets until they become molten balls of rock and metal. The violence of planetary formation defies human comprehension. Imagine objects the size of Texas slamming into each other at speeds of tens of kilometers per second. The energy released in these impacts vaporizes rock, creates magma oceans that cover entire planetary surfaces, and sometimes literally blows worlds apart, only for the fragments to reassemble under their own gravity into new configurations. Earth itself grows through this violent process, accumulating mass from countless impacts over roughly 100 million years. But the most dramatic event in our planet's early history is yet to come. About 30 to 50 million years after Earth's initial formation, an object roughly the size of Mars, APT-Phi, which scientists have named Theia, slams into our still-forming world at an oblique angle. The Mars-sized impact that creates our moon represents one of the most catastrophic events in solar system history. The collision occurs at a speed of approximately 11 kilometers per second, releasing energy equivalent to billions of nuclear weapons. The impact vaporizes both Theia and a large portion of Earth's outer layers, hurling a massive cloud of molten rock and vapor into orbit around our planet. This debris gradually coalesces to form the moon, while the angular momentum from the collision tilts Earth's axis 23.5 degrees, giving us the seasons that make our world habitable for complex life. The outer regions of the solar system tell a different story of planetary formation. Beyond what astronomers call the frost line, the distance from the sun, where water can freeze into ice, a different type of world begins to form. Here, Jupiter emerges as the dominant force, growing so massive that it becomes a failed star. This gas giant forms through a two-stage process that demonstrates the delicate balance between order and chaos in planetary systems. Jupiter begins like the rocky planets, as a solid core of rock, ice, and metal, perhaps 10 to 15 times more massive than Earth. But this core reaches a critical threshold where its gravity becomes strong enough to capture vast amounts of hydrogen and helium directly from the surrounding disk. The process accelerates rapidly as Jupiter's growing mass allows it to sweep up material more efficiently until it becomes a gravitational monster containing more mass than all the other planets combined. The formation of Jupiter has profound consequences for the entire solar system. Its immense gravity disrupts the formation of planets in the asteroid belt, preventing the scattered debris there from coalescing into a world. Jupiter's gravitational influence also affects the delivery of water and organic compounds to the inner planets, either facilitating or hindering the development of conditions suitable for life depending on the precise timing and dynamics of its formation. Saturn follows a similar path to gas giant status, though it never grows quite as massive as Jupiter. The ice giants Uranus and Neptune form in the outer reaches of the solar system, where temperatures are so cold that even methane and ammonia freeze into solid ice. These worlds may have formed closer to the Sun and migrated outward due to gravitational interactions with Jupiter and Saturn, a process that would have dramatically reshaped the architecture of the early solar system. The universe has another surprise for us in the sheer scale of violence that characterizes this early period of solar system evolution. The late heavy bombardment, which occurred roughly 600 million years after the Sun's formation, represents a period of renewed chaos when the gravitational influence of the migrating giant planets destabilized the orbits of countless asteroids and comets. These objects rained down on the inner planets in a cosmic shooting gallery that lasted for several 100 million years. The surfaces of Mercury, Venus, Earth and Mars were resurfaced by this bombardment, with impact rates thousands of times higher than anything the planets experience today. On Earth, the largest impacts created temporary atmospheres of vaporized rock and may have boiled away the oceans multiple times. Yet somehow, life not only survived this cosmic assault, but may have actually benefited from it, as asteroid and comet impacts delivered the water and organic compounds necessary for biological evolution. Here's what's actually happening during this period of apparent destruction. The solar system is learning how to become stable. The chaotic early phase gradually gives way to the more orderly system we observe today, as gravitational interactions settle into long-term equilibrium. The planets clear their orbital zones of debris. Jupiter and Saturn lock into a gravitational resonance that stabilizes their orbits, and the remaining small bodies are either ejected from the system or confined to relatively safe regions like the asteroid belt and Kuiper belt. The transformation from cosmic demolition derby to stable planetary system takes roughly 1 billion years, about 20% of the Sun's current age. But the end result is remarkable. 8 distinct worlds, each shaped by the unique conditions it experienced during formation. Mercury, stripped of most of its outer layers by solar radiation and impacts, becomes a dense ball of iron with only a thin shell of rock. Venus develops a thick atmosphere that traps heat so efficiently that surface temperatures soar higher than those on Mercury despite being farther from the Sunday. Mars grows large enough to develop a substantial atmosphere and possibly even oceans, but its small size means it cannot retain these features indefinitely. The red planet becomes a world of extremes, with the largest volcano and the deepest canyon in the solar system, carved by processes that operated when Mars was young and geologically active. The asteroid belt preserves samples of the original building blocks of planetary formation, scattered fragments that never had the chance to assemble into a full-sized world. The outer solar system becomes the domain of the gas giants, each one a complex system of moons that resembles a miniature solar system. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, span a range of compositions and geological activity that rivals the diversity of the planets themselves. Saturn's moon system includes Titan, with its thick atmosphere and lakes of liquid methane, and tiny Enceladus, which harbors a global ocean beneath its icy crust. The formation of our solar system represents just one example of planetary system architecture, among the thousands now being discovered around other stars. Some systems contain hot Jupiters that orbit closer to their stars than Mercury orbits our Sun, suggesting that planetary migration can sometimes drive gas giants inward rather than outward. Other systems show evidence of violent collisions that occurred much later than our own late heavy bombardment, reminding us that the universe continues to be a dynamic and sometimes destructive place. When we look at the solar system today, with its orderly arrangement of planets following nearly circular orbits in the same plane, it's easy to forget the violence and chaos that created this apparent harmony. Every world bears the scars of its violent birth. Impact craters that pockmark planetary surfaces, tilted axes of rotation caused by massive collisions, and magnetic fields generated by molten cores that are still cooling from the heat of formation. The story of solar system formation teaches us that creation and destruction are intimately linked in the universe. The same gravitational forces that build worlds also tear them apart. The same collisions that seem catastrophically destructive also deliver the raw materials necessary for geological activity and possibly even life. The early solar system was a cosmic laboratory where the fundamental processes of planetary science played out on a grand scale, setting the stage for billions of years of subsequent evolution. We exist in a universe where violence and beauty are two faces of the same cosmic coin. The gentle light of the sun that warms our faces began as nuclear fire ignited by gravitational collapse so violent it outshone nearby stars. The moon that illuminates our nights was born from the most catastrophic impact our planet has ever experienced. The water in our oceans and the carbon in our bodies were delivered by asteroids and comets during a period of bombardment that would have made Earth uninhabitable by modern standards. This is the paradox of planetary formation. It requires destruction to create, chaos to establish order, and violence to build the foundations for peace. The solar system we inhabit today is both the result of and the survivor of cosmic forces so powerful they challenge our ability to comprehend them. Yet from this violence emerged not just worlds, but the possibility of life, intelligence, and the kind of curiosity that drives us to understand our own origins. The birth of our solar system from cosmic violence reminds us that we are the children of stars and the inheritors of processes that operate on scales of space and time that dwarf human experience. But it also demonstrates the remarkable ability of matter to organize itself into structures of increasing complexity and beauty, transforming simple clouds of gas and dust into worlds capable of supporting the very consciousness that seeks to understand them. Imagine standing at the edge of our solar system and looking inward, seeing not just points of light but entire worlds, each one a unique experiment in planetary evolution. 8 major planets orbit our sun, and no two are alike. Each world tells its own story of formation, evolution, and the endless creativity of cosmic forces. From Mercury's scorched surface to Neptune's impossibly fast winds, our planetary neighbors reveal the incredible diversity that emerges when the same basic materials are shaped by different conditions. Let's begin our journey at Mercury, the smallest planet and the one closest to our Sunday. Here's what's really happening on this tiny world. Mercury races around the Sun at 48 kilometers per second, completing one orbit every 88 Earth days. But here's where Mercury gets really strange. It rotates so slowly that one Mercurian day lasts 59 Earth days. This creates the most extreme temperature variations in the solar system. At noon on Mercury's equator, surface temperatures soar to 427 degrees Celsius, hot enough to melt zinc. But step into shadow or wait for the long Mercurian night, and temperatures plummet to minus 173 degrees Celsius, colder than the winter on Mars. The universe has a surprise for us about Mercury. This sun-baked world actually harbors water ice. In permanently shadowed craters at Mercury's poles, where sunlight never penetrates, temperatures remain cold enough to preserve ice deposits that may have existed for billions of years. These ice patches were discovered in 1991 using Earth-based radar, proving that even the most unlikely places in the solar system can hold unexpected treasures. Mercury's surface tells a story of cosmic violence written in craters. The planet bears the scars of billions of years of asteroid and comet impacts, but one feature dominates all others: the Caloris Basin, a massive crater over 1,500 kilometers across. The impact that created Caloris was so powerful that it sent shockwaves completely through the planet, creating a jumbled, fractured landscape on the exact opposite side of Mercury from the impact site. Venus, our nearest planetary neighbor, hides its secrets beneath the thickest atmosphere in the inner solar system. Here's what's actually happening beneath those beautiful cream-colored clouds. Venus experiences a greenhouse effect so extreme that it makes global warming on Earth seem trivial by comparison. The planet's atmosphere consists of 96% carbon dioxide, creating surface pressures 92 times greater than Earth's, equivalent to being crushed under a kilometer of water. The surface of Venus reaches temperatures of 462 degrees Celsius, making it the hottest planet in the solar system despite being farther from the Sun than Mercury. This hellish heat is hot enough to melt lead, zinc, and tin. If you could somehow survive the crushing pressure and toxic atmosphere long enough to look around, you'd see a landscape illuminated by an eerie orange glow, where sulfuric acid rain falls from the sky but evaporates before reaching the ground. But Venus holds an even stranger secret. It spins backward. While most planets rotate in the same direction they orbit the Sun, Venus turns in the opposite direction, taking 243 Earth days to complete one rotation. This means a Venusian day lasts longer than a Venusian year, which takes only 225 Earth days. On Venus, the Sun rises in the west and sets in the east, assuming you could see the Sun through the thick clouds that permanently shroud the remain. The planet's surface, Mars, captures our imagination like no other world, because it's the planet most similar to Earth, yet different enough to remind us how precious our own world truly is. The red planet gets its color from iron oxide, rust, covering much of its surface, evidence of a time when liquid water and oxygen were more abundant in the Martian atmosphere. Mars experiences seasons similar to Earth's because its axis is tilted 25 degrees, just 2 degrees more than our own planet's tilt. Here's what makes Mars truly remarkable. This is a world where ancient rivers once flowed, and where the largest volcano in the solar system still stands. Olympus Mons rises 21 kilometers above the surrounding plains, nearly 3 times taller than Mount Everest. This massive shield volcano covers an area roughly the size of Arizona and represents one of the most impressive geological features in the solar system. The fact that such enormous volcanoes could form on Mars tells us that the planet's crust doesn't move like Earth's, allowing volcanic hotspots to build mountains of unprecedented size. Mars also hosts Valles Marineris, a canyon system that stretches over 4,000 kilometers across the planet's surface, nearly the width of the United States. In some places, this Grand Canyon reaches depths of 7 kilometers and widths of 200 kilometers. Standing on the rim of Valles Marineris, you wouldn't be able to see the opposite side due to the curvature of Mars itself. The red planet experiences dust storms unlike anything on Earth. These Martian storms can engulf the entire planet for months at a time, driven by temperature differences between the polar ice caps and the equatorial regions. During global dust storms, the Martian sky turns dark as midnight, and surface features completely disappear under the swirling dust clouds. Jupiter reigns as the king of planets, a gas giant so massive that it contains more matter than all the other planets combined. Here's what's truly happening inside Jupiter. This is a failed star, a world that came tantalizingly close to igniting nuclear fusion in its core. If Jupiter had been about 80 times more massive, it would have become a star, making our solar system a binary star system instead of a single star system with planets. Jupiter radiates more energy than it receives from the Sun, generating heat through the slow gravitational compression of its massive atmosphere. The planet's Great Red Spot, a storm larger than 3 Earths, has been raging for at least 350 years, possibly much longer. This massive hurricane is powered by Jupiter's internal heat and maintained by the planet's rapid rotation, which causes the equatorial regions to bulge outward and creates powerful atmospheric dynamics. The universe has another surprise for us about Jupiter. This giant planet acts as a cosmic vacuum cleaner, using its immense gravity to capture or deflect asteroids and comets that might otherwise threaten the inner planets. Jupiter's gravitational influence has shaped the entire solar system, preventing the formation of a planet in the asteroid belt, and probably protecting Earth from frequent catastrophic impacts. Jupiter commands an empire of at least 79 known moons, including the 4 Galilean satellites discovered by Galileo in 1610. Europa, one of these moons, hides an ocean beneath its icy crust that contains twice as much water as all Earth's oceans combined. This subsurface sea, kept liquid by tidal heating from Jupiter's gravity, represents one of the most promising places to search for life beyond Earth. Saturn graces our solar system with the most spectacular ring system known to science. These rings extend 282,000 kilometers from the planet, but average only 10 meters thick, making them proportionally thinner than a sheet of paper. The rings consist of billions of ice particles, ranging from tiny grains to house-sized boulders, all held in precise formation by the gravitational influence of shepherd moons that orbit just inside and outside the ring system. Here's what's actually happening in Saturn's rings. We're witnessing gravitational physics on a grand scale. Each particle in the rings follows its own individual orbit around Saturn, but gravitational resonances with the planet's moons create gaps, waves, and spiral structures throughout the ring system. The Cassini division, a prominent gap in the rings, exists because particles orbiting in that region would complete exactly 2 orbits for every 1 orbit of the Moon, Mimas, creating a gravitational resonance that clears the region of debris. Saturn's largest moon, Titan, represents one of the most Earth-like worlds in the solar system, despite surface temperatures of -179 degrees Celsius. Titan possesses a thick atmosphere, composed primarily of nitrogen, just like Earth's atmosphere. But instead of water, rain, and rivers, Titan experiences weather systems driven by liquid methane and ethane. Lakes of liquid hydrocarbons dot Titan's surface, creating an alien version of Earth's water cycle. Uranus rolls through space like a cosmic bowling ball, spinning on its side due to an ancient collision that knocked the planet over. This ice giant experiences the most extreme seasons in the solar system, with each hemisphere enduring 21 years of continuous sunlight, followed by 21 years of darkness. As Uranus orbits the Sunday, the planet's unusual orientation creates weather patterns unlike those on any other world. Here's what makes Uranus truly mysterious. This ice giant radiates virtually no internal heat. Unlike Jupiter, Saturn, and Neptune, something catastrophic happened in Uranus's past that affected its internal structure, possibly the same collision that tilted the planet on its side. The planet's magnetic field provides additional clues to its unusual nature. It's tilted 59 degrees from the planet's rotational axis and offset from the planet's center, suggesting a complex internal structure unlike any other world. Neptune, the windiest planet in the solar system, generates storms with velocities reaching 2,100 kilometers per hour, despite receiving only 1/1000th of Earth's solar energy. This seems impossible at first glance. How can a world so far from the Sun that it receives almost no solar heating drive such powerful atmospheric dynamics? The answer lies in Neptune's internal heat source. Like Jupiter and Saturn, Neptune radiates more energy than it receives from the Sun, suggesting powerful internal heat sources that drive the planet's dynamic atmosphere. The exact mechanism behind this internal heating remains one of planetary science's unsolved mysteries, but it demonstrates that the outer solar system is far more active and dynamic than we might expect. Neptune's largest moon, Triton, adds another layer of mystery to this distant world. Triton orbits Neptune backward, I-80, in the opposite direction to the planet's rotation, and follows a circular orbit despite being captured from the Kuiper Belt sometime in the distant past. Triton shows signs of geological activity, with nitrogen geysers erupting from its south polar region, proving that even the coldest, most distant worlds in our solar system can surprise us with their complexity. The universe reveals its creativity through the incredible diversity of these 8 worlds. Each planet represents a different solution to the basic problem of how matter organizes itself under the influence of gravity, heat, and time. The rocky planets show us how solid surfaces evolve through volcanism, impact cratering, and atmospheric erosion. The gas giants demonstrate how atmospheres can become worlds unto themselves with weather systems that dwarf anything Earth experiences. Here's what's truly remarkable about our planetary family. Despite Forming from the same initial cloud of gas and dust, no two worlds evolved along identical paths. Distance from the Sun, planetary mass, rotational period, magnetic field strength, and the presence or absence of large moons all contributed to making each world unique. Mars might have evolved differently if it had been more massive, retaining its atmosphere and surface water. Venus might have remained habitable if it had rotated faster, preventing the runaway greenhouse effect that turned it into a hellish oven. Each planet serves as a natural laboratory for understanding planetary science. Mercury teaches us about the effects of extreme solar heating and the importance of magnetic fields for protecting atmospheres. Venus shows us what happens when greenhouse effects run out of control. Mars demonstrates how small worlds lose their atmospheres over geological time. The gas giants reveal the physics of massive atmospheric systems and the complex gravitational dynamics that govern systems of multiple moons. When we look at these 8 worlds, we're seeing not just our immediate cosmic neighbors, but examples of the kinds of planets that probably exist throughout the galaxy. Every star system tells its own story of planetary formation and evolution, but the fundamental processes we observe in our solar system, gravitational accretion, atmospheric evolution, magnetic field generation, and tidal heating, operate wherever worlds form around stars. The diversity of our planetary family reminds us that Earth's ability to support life depends on countless factors working in harmony. Our planet occupies the right distance from the Sun for liquid water to exist, possesses the right mass to retain an atmosphere, has a magnetic field that protects us from harmful solar radiation, and benefits from a large moon that stabilizes our rotational axis. Change any one of these factors significantly, and Earth might have evolved to resemble Venus, Mars, or one of the other worlds that surround us. Yet this diversity also gives us hope for finding life elsewhere in the universe. If our solar system can produce 8 completely different worlds from the same starting materials, imagine the variety of planets that must exist among the thousands of star systems now being discovered. Some of those distant worlds may have found their own paths to habitability, developing conditions suitable for life in ways we're only beginning to imagine. The 8 worlds of our solar system represent both our cosmic family and our future destinations. Each planet offers unique scientific treasures and engineering challenges for future human exploration. As we prepare to become an interplanetary species, these diverse worlds will serve as stepping stones to understanding how life might arise and evolve on planets throughout the galaxy. The year 1610 marked the beginning of a revolution that would forever change humanity's understanding of our place in the cosmos. Galileo Galilei, a mathematics professor in Padua, aimed his primitive telescope at Jupiter and made a discovery that demolished 2,000 years of accepted wisdom about the universe. Here's what actually happened on that January night that transformed our cosmic perspective. Galileo observed 4 small stars near Jupiter that seemed to change position from night to night. Within a week of careful observation, he realized these weren't stars at all. They were moons orbiting the giant planet. This single observation shattered the Earth-centered model of the universe that had dominated human thinking since ancient times. If Jupiter could have moons orbiting around it, then not everything in the cosmos revolved around Earth. Galileo had discovered the first planetary system beyond our own, proving that the universe was far more complex and wonderful than anyone had imagined. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, became the first worlds beyond Earth that humans could study in detail. But Galileo's telescope revealed even more revolutionary secrets. When he turned his instrument toward Venus, he observed that the planet showed phases, just like the moon, appearing as a thin crescent when close to Earth and nearly full when on the far side of the Sunday. This observation provided decisive proof that Venus orbited the Sun, not Earth, supporting the sun-centered model proposed by Nicholas Copernicus decades earlier. The universe had a surprise for early telescopic observers. Saturn appeared to have handles or ears protruding from its sides. Galileo's telescope wasn't powerful enough to resolve Saturn's rings clearly, so he interpreted what he saw as two large moons attached to the planet. It wasn't until 1659 that Christian Huygens, using a better telescope, realized that Saturn was surrounded by a thin, flat ring that didn't touch the planet anywhere. Johannes Kepler, working with precise observations made by Tycho Brahe, solved the mathematical puzzle of planetary motion that had baffled astronomers since ancient times. Here's what Kepler discovered that changed everything. Planets don't follow perfect circles around the Sun, as everyone had assumed, but rather elliptical orbits with the Sun at one focus of the ellipse. This revelation explained why planets sometimes appear to speed up and slow down in their journeys across the sky. They actually do move faster when closer to the Sun, and slower when farther away. Kepler's three laws of planetary motion provided the mathematical foundation for understanding how gravity shapes the solar system. His first law described the elliptical nature of planetary orbits. His second law revealed that planets sweep out equal areas in equal times, explaining the variable speeds of planetary motion. His third law established a precise mathematical relationship between a planet's orbital period and its distance from the Sun, providing the tools needed to map the true scale of the solar system. Isaac Newton transformed Kepler's mathematical descriptions into a universal theory of gravitation that explained not just planetary motion, but the behavior of all matter in the universe. Here's what Newton realized that completed the revolution. The same force that causes an apple to fall from a tree also keeps the moon in orbit around Earth, and the planets in orbit around the Sunday. Gravity operates across vast distances of space, creating an invisible architecture that holds the solar system together. Newton's law of universal gravitation revealed that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This elegant mathematical relationship explained not just planetary orbits, but also the tides, the precession of Earth's axis, and the complex gravitational dance between multiple bodies in space. The 18th and 19th centuries brought increasingly powerful telescopes and more sophisticated mathematical techniques that revealed the solar system's true complexity. William Herschel discovered Uranus in 1781, doubling the known size of the solar system overnight. This ice giant, barely visible to the naked eye, had been hiding in plain sight for thousands of years, mistaken for a dim star by earlier observers. Herschel's discovery demonstrated that the solar system was far larger than anyone had imagined. Uranus orbits the Sun at a distance of nearly 3 billion kilometers, taking 84 Earth years to complete one orbit. The discovery of this distant world raised profound questions. If one new planet could remain hidden for so long, how many other worlds might be waiting to be discovered in the outer reaches of the solar system? The universe provided an answer when mathematical analysis of Uranus's orbit revealed gravitational perturbations that could only be explained by the presence of another, even more distant planet. In 1846, Neptune was discovered exactly where mathematical calculations predicted it should be, proving that Newton's law of gravitation could be used not just to explain known phenomena, but to predict the existence of unknown worlds. Here's what makes the discovery of Neptune truly remarkable. This planet was found with mathematics before it was seen with telescopes. Urbain Le Verrier in France and John Couch Adams in England independently calculated where the unknown planet should be located, based on its gravitational effects on Uranus. When Johann Gaia pointed his telescope at the predicted position, he found Neptune within 1 degree of the calculated location. The space age began on October 4th, 1957, when the Soviet Union launched Sputnik 1, a beach ball-sized satellite that changed everything. This 83-kilogram metal sphere, beeping radio signals as it orbited Earth every 96 minutes, demonstrated that humans could send objects beyond our planet's atmosphere. The space race had begun, and the solar system would never be the same. Within 4 years of Sputnik's launch, humans had sent robotic explorers to the Moon and Venus. Luna 3 provided the first images of the Moon's far side in 1959, revealing a heavily cratered landscape unlike the familiar near side visible from Earth. Venera 1 attempted the first planetary flyby in 1961, though contact was lost before it reached Venus. These early missions were primitive by modern standards, but they proved that interplanetary travel was possible. The 1960s brought increasingly sophisticated missions that revolutionized our understanding of the solar system. Mariner 2's successful flyby of Venus in 1962 revealed that our nearest planetary neighbor was a hellish world with surface temperatures hot enough to melt lead. This discovery shattered romantic notions of Venus as Earth's twin, instead revealing a cautionary tale about runaway greenhouse effects. Mariner 4's flyby of Mars in 1965 provided the first close-up images of the red planet, showing a cratered, apparently lifeless world that looked more like the Moon than the Earth-like planet many had hoped to find. The 21 images returned by Mariner 4 covered less than 1% of Mars's surface, but they were enough to dispel fantasies about Martian civilizations and canal systems. Here's what's remarkable about these early space missions. They were accomplished with technology less sophisticated than a modern smartphone. The computers that guided these spacecraft had less processing power than a digital watch, yet they successfully navigated millions of kilometers through space to encounter distant worlds with incredible precision. The 1970s marked the golden age of solar system exploration, with the launch of Voyager 1 and 2 in 1977. These twin spacecraft were designed to take advantage of a rare alignment of the outer planets that occurs only once every 176 years. The Grand Tour mission allowed each Voyager to use gravitational assists from one planet to reach the next, conducting an unprecedented survey of Jupiter, Saturn, Uranus, and Neptune. Voyager 1's encounter with Jupiter in 1979 revealed active volcanoes on the moon Io, the first volcanic activity discovered beyond Earth. The spacecraft's images showed sulfur plumes erupting hundreds of kilometers above Io's surface, powered by tidal heating from Jupiter's immense gravity. This discovery proved that the outer solar system was far more geologically active than anyone had expected. The Voyager missions transformed our understanding of Saturn's ring system, revealing thousands of individual ringlets where ground-based telescopes had seen only a few broad bands. The spacecraft discovered shepherd moons that use their gravity to maintain sharp ring edges, spoke-like features that rotate with Saturn's magnetic field, and intricate braided structures that challenge theoretical models of ring dynamics. Voyager 2's encounters with Uranus and Neptune in the 1980s provided our first and only close-up views of these distant ice giants. The spacecraft revealed that Uranus has a complex magnetic field tilted 59 degrees from its rotational axis, while Neptune possesses the fastest winds in the solar system despite receiving almost no energy from the distant Sunday. When Voyager 1 crossed into interstellar space in 2012, it carried a golden record containing sounds and images from Earth, a message to any alien civilization that might encounter this human-made object drifting between the stars. The spacecraft continues to transmit data about the interstellar medium, providing our first direct measurements of the space between star systems. The 1990s brought the Hubble Space Telescope, which transformed astronomy by providing crystal-clear images free from atmospheric distortion. Hubble's observations revealed the complex geology of planetary surfaces, the intricate structure of ring systems, and the atmospheric dynamics of gas giant planets. The telescope's ability to observe planets at different wavelengths of light revealed features invisible to ground-based telescopes. The Galileo mission to Jupiter, which operated from 1995 to 2003, provided the first long-term study of a gas giant planet and its moons. The spacecraft's atmospheric probe plunged directly into Jupiter's atmosphere, revealing wind speeds exceeding 600 kilometers per hour and providing direct measurements of the planet's composition. Galileo's observations of Europa revealed strong evidence for a subsurface ocean, making this ice-covered moon one of the most promising places to search for life beyond Earth. The Cassini-Huygens mission to Saturn represented the most ambitious planetary exploration project ever undertaken. Launched in 1997, Cassini spent 13 years studying the Saturn system, revealing geysers erupting from Enceladus's south pole, seasonal changes in Titan's hydrocarbon lakes, and the complex dynamics of Saturn's ring system. The Huygens probe, provided by the European Space Agency, successfully landed on Titan's surface in 2005, sending back images and data from the first landing on a moon in the outer solar system. Here's what makes the Cassini mission truly extraordinary. The spacecraft revealed that several of Saturn's moons harbor subsurface oceans that could potentially support life. Enceladus, barely 500 kilometers in diameter, shoots geysers of water vapor and organic compounds 160 kilometers into space from fractures near its south pole. These tiger stripes, as scientists call them, provide direct access to an underground ocean that may have existed for billions of years. The Mars exploration program has transformed our understanding of the red planet through increasingly sophisticated rovers and orbiters. The twin Mars exploration rovers, Spirit and Opportunity, launched in 2003, were designed for 90-day missions but operated for years beyond their planned lifetimes. Opportunity continued working for almost 15 years, driving over 45 kilometers across the Martian surface and proving that liquid water once flowed freely on Mars. The Curiosity rover, which landed in Gale Crater in 2012, carries a nuclear-powered laboratory capable of analyzing rock samples with precision rivaling Earth-based instruments. Curiosity's discoveries include evidence of ancient stream beds, seasonal variations in atmospheric methane, and organic compounds preserved in Martian rocks for billions of years. These findings suggest that Mars once had conditions suitable for microbial life, and may still harbor subsurface organisms today. The universe has revealed its secrets through increasingly powerful space telescopes that can observe planets around other stars. The Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets by detecting the tiny dimming of starlight when planets pass in front of their host stars. These discoveries revealed that planetary systems are common throughout the galaxy, and that many stars host Earth-sized worlds in their habitable zones. The James Webb Space Telescope, which began observations in 2022, possesses the capability to analyze the atmospheres of exoplanets, potentially detecting signs of life on distant worlds. This revolutionary instrument can observe planets forming around young stars, study the composition of planetary atmospheres, and search for biosignatures, chemical indicators of biological processes, in the spectra of exoplanet atmospheres. Here's what's truly remarkable about our exploration of the solar system. We've sent robotic ambassadors to every major world in our cosmic neighborhood. Mercury has been visited by Mariner 10 and Messenger, revealing a planet with a surprisingly large iron core and evidence of past volcanic activity. Venus has been studied by dozens of Soviet and American missions, including the Venera landers that successfully reached the planet's hellish surface and transmitted images before succumbing to the extreme conditions. Mars has become humanity's most intensively studied planet after Earth, with orbiters mapping the surface in extraordinary detail and rovers exploring ancient lake beds, river deltas, and volcanic regions. The red planet serves as our testing ground for technologies and techniques that will eventually enable human exploration of other worlds. The asteroid belt has been explored by missions like Dawn, which orbited both Vesta and Ceres, revealing that these small worlds are far more complex and geologically diverse than expected. Ceres, the largest asteroid, harbors organic compounds and possibly subsurface brine deposits, while Vesta shows evidence of ancient lava flows and a complex geological history. Comets, those pristine time capsules from the early solar system, have been studied by missions that have flown through their tails, impacted their surfaces, and even landed on their nuclei. The Rosetta mission spent 2 years orbiting Comet 67P Churyumov-Gerasimenko, revealing that comets are complex, dynamic objects with active geology driven by solar heating. The outer solar system continues to surprise us with each new mission. New Horizons flyby of Pluto in 2015 revealed a geologically active world with nitrogen glaciers, methane dunes, and a heart-shaped plain that captured the public imagination. This distant dwarf planet, once considered a frozen ice ball, showed evidence of atmospheric processes and possibly even subsurface liquid water. Here's what the heroes of solar system exploration have taught us. The universe is far stranger, more beautiful, and more complex than we ever imagined. Every world we've visited has defied our expectations, revealing unique geology, chemistry, and physical processes that expand our understanding of how planets work. The same spacecraft that showed us active volcanoes on Io also revealed subsurface oceans on Europa, proving that the conditions for life might exist in places we never thought to look. The exploration of our solar system represents humanity's greatest adventure story, a tale of curiosity, ingenuity, and perseverance that spans centuries. From Galileo's first telescopic observations to modern robotic missions exploring the outer reaches of our cosmic neighborhood, each discovery has built upon previous knowledge, while opening new questions that drive us to explore further. The heroes who shattered our Earth-centered view of the cosmos, Galileo, Kepler, Newton, and countless others, began a revolution that continues today. Modern mission scientists and engineers carry forward their legacy of discovery, using increasingly sophisticated tools to explore worlds that early astronomers could barely imagine. Each spacecraft launched, each image returned, and each scientific discovery adds another chapter to the greatest story ever told, our quest to understand our place in the universe. The robotic explorers we've sent throughout the solar system serve as our eyes and hands, extending human presence to worlds we cannot yet visit in person. They've shown us that the solar system is not a collection of dead rocks orbiting the sun, but a dynamic, interconnected system where geology, chemistry, and possibly biology continue to operate on every world we've studied. These missions have also demonstrated the incredible precision and reliability of modern spacecraft engineering. Navigating billions of kilometers through space to encounter fast-moving targets with precision measured in kilometers requires mathematical calculations and engineering execution that push the boundaries of human capability. The fact that we can routinely send spacecraft to other worlds and receive detailed scientific data represents one of our species' greatest technological achievements. The heroes who opened the solar system to human exploration include not just the famous names from history books, but also the thousands of scientists, engineers, and technicians who design, build, and operate the spacecraft that serve as our ambassadors to other worlds. Their work has transformed our understanding of planetary science, revealed the conditions necessary for life, and shown us that the solar system is our natural laboratory for understanding how worlds form and evolve throughout the universe. As we stand on the threshold of human exploration beyond Earth, we carry forward the legacy of all those who shattered the sky and revealed the true nature of our cosmic neighborhood. The same curiosity that drove Galileo to point his telescope at Jupiter now drives us to plan missions to Mars, Europa, and beyond. The mathematical precision that allowed Kepler to map planetary orbits now guides spacecraft to distant worlds with accuracy that would have seemed magical to earlier generations. The exploration of our solar system has shown us that we live in a universe of incredible diversity and beauty, where each world tells its own story of formation, evolution, and the endless creativity of cosmic forces. The heroes who made these discoveries possible have given us not just knowledge, but inspiration, proof that human curiosity and ingenuity can overcome any obstacle and unlock the secrets of the cosmos itself. In the deepest reaches of our solar system, where sunlight barely penetrates the cosmic darkness, some of the most profound mysteries in planetary science continue to whisper their secrets to those patient enough to listen. These are not the obvious puzzles that catch headlines, but the subtle enigmas that challenge our fundamental understanding of how worlds work. From hidden oceans beneath alien ice to storms that maintain impossible geometric shapes, the outer solar system holds riddles that may reshape our understanding of physics, chemistry, and life itself. Beneath Europa's 15-kilometer thick ice shell lies perhaps the most tantalizing mystery in our solar system, an ocean that has remained liquid for billions of years. Here's what's actually happening beneath that frozen surface. Jupiter's immense gravity stretches and compresses Europa as the Moon follows its elliptical orbit, generating enough heat through tidal friction to keep an ocean liquid despite temperatures that would freeze any surface water in seconds. This hidden sea contains approximately twice as much water as all Earth's oceans combined, but that's not what makes it so fascinating to scientists. The ocean has been stable for potentially billions of years, long enough for life to evolve from simple chemicals into complex organisms. Unlike Earth's oceans, which are heated by sunlight and lose energy to space, Europa's ocean is heated from below by the Moon's rocky core and insulated from above by kilometers of ice. The universe has a surprise for us about Europa's ocean. It may be in direct contact with the Moon's rocky mantle, allowing chemical interactions that could provide the energy sources necessary for life. On Earth, some of the most primitive and hardy life forms thrive around underwater volcanic vents, deriving energy not from sunlight but from chemical reactions between water and hot rock. Europa's ocean floor may host similar hydrothermal systems, creating oases of warmth and chemical energy in the perpetual darkness beneath the ice. But Europa's ocean presents a profound puzzle that challenges our understanding of how moons evolve over time. The ice shell shows evidence of recent geological activity, cracks, ridges, and chaotic terrain that suggest the surface has been reshaped within the last few million years. If the ocean has existed for billions of years, why does the surface appear so young? The answer may lie in Europa's complex relationship with Jupiter's radiation environment and the dynamic processes that drive material exchange between the ocean and the ice shell above. Enceladus, Saturn's sixth-largest moon, presents an even more dramatic mystery. This tiny world, barely 500 kilometers in diameter, shoots geysers of water vapor and organic compounds 160 kilometers into space from fractures near its south pole called tiger stripes. Here's what makes this phenomenon truly puzzling. Enceladus is far too small to maintain geological activity through radioactive decay, yet it clearly possesses an active subsurface ocean and ongoing geological processes. The geysers of Enceladus provide direct access to an alien ocean without the need to drill through kilometers of ice. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition and discovering not just water vapor, but also organic compounds, nitrogen, and trace amounts of molecular hydrogen, all potential ingredients for life. The chemistry of these plumes suggests hydrothermal activity on Enceladus's ocean floor, similar to the underwater vents where life may have first emerged on Earth. But the tiger stripes themselves present a geometric mystery that defies easy explanation. These parallel fractures are spaced with mathematical precision, separated by exactly 35 kilometers along the entire length of each stripe. This regular spacing suggests that the formation of these fractures is controlled by some fundamental physical process, but no current model can fully explain why they maintain such perfect geometric relationships. Saturn's north polar hexagon represents perhaps the most visually striking mystery in the solar system. This six-sided storm spans 30,000 kilometers, large enough to engulf two Earths, and maintains its geometric shape despite wind speeds reaching 500 kilometers per hour. Here's what's truly baffling about this phenomenon. Hexagons don't occur naturally in fluid dynamics under normal circumstances. Atmospheric storms tend to be circular, elliptical, or irregular, not perfectly geometric. The hexagon has persisted for decades, photographed by both Voyager and Cassini spacecraft separated by 30 years. Laboratory experiments have shown that rotating fluids can form polygonal patterns under specific conditions involving differential rotation rates, but scaling these effects up to planetary atmospheres requires mechanisms that we don't fully understand. The hexagon may be teaching us something fundamental about fluid dynamics that applies not just to gas giant atmospheres, but to weather systems throughout the universe. Mars presents the greatest mystery of planetary evolution. Where did its power, water, disappear? Ancient riverbeds, lake beds, and mineral deposits prove that liquid water once flowed freely across the Martian surface for hundreds of millions of years. Valley networks carved by flowing water extend across vast regions of the planet, while lake deposits in craters show evidence of standing water that persisted for thousands or even millions of years. Here's what makes the loss of Martian water so puzzling. The planet once had a thick enough atmosphere to support liquid water at its surface, but today that atmosphere is so thin that water would instantly boil away even at the lowest elevations. The current atmospheric pressure on Mars is less than 1% of Earth's, equivalent to the pressure at an altitude of 35 kilometers above Earth's surface. Scientists suspect that Mars lost most of its atmosphere to space when its magnetic field weakened, allowing solar wind to strip away the protective gases that once supported a more hospitable climate. But the timeline and mechanisms of this atmospheric loss remain mysterious. Did Mars lose its atmosphere gradually over billions of years, or did catastrophic events strip it away more quickly? The answer may determine whether life had enough time to evolve on the red planet. Recent discoveries have made the Martian water mystery even more complex. The MAVEN orbiter has detected hydrogen escaping from Mars's upper atmosphere, confirming that water continues to be lost to space today. But radar observations have also revealed vast quantities of water ice buried beneath the Martian surface, suggesting that not all of the planet's water disappeared into space. Some may have been sequestered underground, where it could potentially support subsurface life. Venus spins backward compared to most planets, taking 243 Earth days to complete one rotation while orbiting the Sun every 225 days. This means a Venusian day lasts longer than a Venusian year, and the Sun rises in the west and sets in the east. Here's what makes Venus's retrograde rotation so mysterious. Computer simulations of planetary formation don't naturally produce backward-spinning worlds. Several theories attempt to explain Venus's unusual rotation. A massive impact early in the planet's history could have knocked it over, causing it to spin backward. Alternatively, gravitational interactions with the Sun might have gradually slowed Venus's rotation till it reversed direction. Atmospheric tides, IS, caused by the Sun heating Venus's thick atmosphere, might also contribute to the planet's slow, backward spin. But Venus holds even deeper mysteries beneath its shroud of sulfuric acid clouds. Despite surface temperatures hot enough to melt lead, Venus shows evidence of recent volcanic activity that suggests the planet may still be geologically active. Radar images reveal vast volcanic plains, massive shield volcanoes, and complex tectonic features that hint at ongoing geological processes. Yet, we have no direct evidence of current volcanism, leaving the question of Venus's geological activity tantalizingly unresolved. Uranus radiates virtually no internal heat, unlike the other gas giants, suggesting something catastrophic happened in its past that affected its internal structure. Jupiter, Saturn, and Neptune all emit more energy than they receive from the Sun, powered by the slow gravitational compression of their massive interiors. Uranus, however, radiates less energy than it receives, as if its internal heat source has been turned off. The planet's unusual magnetic field provides additional clues to its mysterious nature. Unlike other planets, where magnetic fields align roughly with rotational axes, Uranus's magnetic field is tilted 59 degrees from its rotational axis and offset from the planet's center. This suggests a complex internal structure unlike any other world, possibly the result of the same collision that knocked the planet on its side. Here's what makes Uranus's magnetic field particularly puzzling. It behaves more like the magnetic field of a terrestrial planet than a gas giant. The field appears to be generated in the planet's mantle, a layer of water, methane, and ammonia ices, rather than in a metallic hydrogen core like Jupiter and Saturn. This discovery has forced scientists to reconsider how magnetic fields are generated in ice giant planets. Neptune generates the fastest winds in the solar system, despite receiving only 1/1000th of Earth's solar energy. Winds in Neptune's atmosphere reach velocities of 2,100 kilometers per hour, faster than the speed of sound on Earth. Here's what's truly mysterious about this phenomenon. Conventional meteorology suggests that wind speeds should be proportional to the energy input from the Sun, but Neptune's winds are actually faster than those on Jupiter, which receives 25 times more solar energy. The source of Neptune's internal heat remains one of planetary science's unsolved puzzles. The planet radiates 2.5 times more energy than it receives from the Sun, suggesting powerful internal heat sources that drive its dynamic atmosphere. Possible explanations include radioactive decay in the planet's core, continued gravitational compression from its formation, or even phase transitions in the exotic ices that make up its interior. Neptune's largest moon, Triton, adds another layer of mystery to this distant system. Triton orbits Neptune backward and shows signs of geological activity despite being one of the coldest objects in the solar system. Nitrogen geysers erupting from Triton's south polar region suggest subsurface heating mechanisms that we don't fully understand. The Moon's retrograde orbit indicates that it was captured from the Kuiper belt, but the physics of how such a large object could be captured into a stable orbit remain unclear. The asteroid belt between Mars and Jupiter contains millions of rocky fragments that tell the story of planetary formation, but these ancient remnants also hold mysteries that challenge our understanding of early solar system evolution. Ceres, the largest asteroid and now classified as a dwarf planet, harbors organic compounds and possibly subsurface brine deposits, despite being located far from the Sun in a region where liquid water shouldn't exist. Here's what's surprising about Ceres. This small world shows evidence of recent geological activity, including bright spots that may be salt deposits left behind by evaporating brine. The source of this subsurface liquid and the mechanisms that drive geological activity on such a small, cold world remain mysterious. Ceres may be teaching us that the conditions for liquid water, and possibly even life, extend much farther from the Sun than we previously thought. The mysteries that whisper in the dark corners of our solar system remind us how much we still don't understand about the worlds that surround us. Each puzzle reveals the limitations of our current knowledge while pointing toward new discoveries that may revolutionize our understanding of planetary science. These enigmas drive the development of new missions, instruments, and theories that push the boundaries of human knowledge. The hidden oceans of Europa and Enceladus may harbor life forms unlike anything on Earth, adapted to environments of perpetual darkness and extreme cold. The geometric storms of Saturn and the backward rotation of Venus challenge our understanding of atmospheric and planetary dynamics. The missing water of Mars and the impossible winds of Neptune hint at physical processes that operate on scales and timescales far beyond human experience. These mysteries also remind us that the universe is under no obligation to be simple or easy to understand. The same physical laws that govern motion on Earth also operate throughout the solar system, but they can produce phenomena so strange and beautiful that they stretch our ability to comprehend them. Each mystery solved leads to new questions, ensuring that the exploration of our solar system will continue to surprise and challenge us for generations to come. As we develop the technology to visit these mysterious worlds in person, we may finally find answers to questions that have puzzled scientists for decades. Robot submarines may explore Europa's hidden ocean. Atmospheric probes may unravel the secrets of Saturn's hexagonal storm, and sample return missions may bring pieces of these distant worlds back to Earth for detailed analysis. But perhaps the greatest mystery of all is whether we are alone in our cosmic neighborhood. The subsurface oceans of Europa and Enceladus, the organic compounds on Ceres, and the methane in Titan's atmosphere all hint at the possibility that life may have found ways to survive and thrive in environments that seem impossibly hostile to Earth-based life. The mysteries that whisper in the dark may ultimately whisper the answer to the most profound question we can ask: are we alone in the universe? The future of solar system exploration stretches before us like an uncharted ocean, filled with destinations that will transform humanity from a single planet species into citizens of the cosmos. Within the next few decades, we will witness adventures that surpass even the most ambitious science fiction dreams. Humans walking on Mars, submarines exploring alien oceans, and robotic miners extracting resources from asteroids to fuel our expansion across the solar system. The Artemis program represents humanity's next giant leap, aiming to establish a permanent human presence on the Moon by 2030. Here's what's actually happening with this ambitious project. We're not just returning to the Moon for brief visits like the Apollo missions, but building the infrastructure for sustained human habitation on another world. The Lunar Gateway, a space station in orbit around the Moon, will serve as a staging point for surface operations and a testbed for the life support systems we'll need for Mars exploration. The south pole of the Moon has become our primary target because of a remarkable discovery. Water ice exists in permanently shadowed craters that haven't seen sunlight for billions of years. These lunar ice deposits could provide drinking water, breathable oxygen, and rocket fuel for missions to Mars and beyond. Here's what makes this discovery revolutionary. Instead of carrying all our water from Earth at enormous cost, we can harvest it directly from the Moon, making lunar bases economically sustainable. Lunar mining operations will extract not just water, but also rare metals and helium-3, an isotope that could power fusion reactors on Earth. The Moon's low gravity and lack of atmosphere make it an ideal location for launching missions to other worlds. Spacecraft departing from the lunar surface require only a tiny fraction of the energy needed to escape from Earth's deep gravitational well. But the Moon serves another crucial purpose in our cosmic expansion. It's our training ground for living on other worlds. The psychological challenges of isolation, the engineering problems of maintaining life support systems, and the medical issues of reduced gravity, all these obstacles must be solved on the Moon before we can safely send humans to Mars. Mars beckons as humanity's next great destination, with multiple space agencies planning crewed missions in the 2030 to 2040 timeframe. Here's what makes Mars exploration so compelling. This is a world where life may have existed in the past and might still survive today in subsurface environments. Finding life on Mars would answer one of the most profound questions in science and could provide insights into how life begins and evolves throughout the universe. The journey to Mars presents challenges that dwarf anything humans have attempted before. The trip takes 6 to 9 months each way, depending on the alignment of the planets. During this time, astronauts will be exposed to cosmic radiation levels far higher than anything experienced on Earth or even in Earth orbit. Solar flares and galactic cosmic rays pose serious health risks that we're only beginning to understand. Here's what's remarkable about current Mars mission planning. We're developing technologies that will allow the first human expeditions to live off the land rather than relying entirely on supplies from Earth. The MOXIE experiment on the Perseverance rover has already demonstrated that oxygen can be extracted from the Martian atmosphere. Future missions will land automated systems years before humans arrive, producing fuel, water, and building materials from local resources. The first human settlements on Mars will likely be established near the polar ice caps, or in regions where subsurface water has been detected by orbital surveys. These bases will gradually expand into self-sustaining colonies, capable of supporting thousands of residents. Terraforming Mars, gradually transforming its atmosphere to support human life without pressure suits, represents a challenge that could take centuries but would create humanity's first backup planet. Asteroid mining promises to revolutionize both space exploration and Earth's economy. A single metallic asteroid could contain more platinum than has ever been mined on Earth, while water-rich asteroids could serve as refueling stations for deep space missions. Here's what makes asteroid mining so potentially profitable. Launching materials from Earth costs thousands of dollars per kilogram, but extracting them from asteroids in zero gravity requires far less energy. The first asteroid mining operations will target near-Earth asteroids that are easier to reach than the Moon. Robotic miners will extract water, precious metals, and rare Earth elements, transporting them to orbital facilities where they can be processed and distributed throughout the solar system. These space-based industries will make large-scale construction projects possible, from massive space stations to interplanetary spacecraft that would be impossible to launch from Earth. Water extracted from asteroids will become the most valuable commodity in space, providing life support for astronauts and serving as rocket fuel when split into hydrogen and oxygen. Asteroid water could supply propellant depots throughout the solar system, enabling spacecraft to refuel for journeys to the outer planets without carrying all their fuel from Earth. The search for life focuses increasingly on the icy moons of Jupiter and Saturn, where subsurface oceans may have remained stable for billions of years. Europa Clipper, launching in 2024, will conduct detailed reconnaissance of Jupiter's ice-covered moon, mapping the thickness of its ice shell and searching for locations where the underlying ocean might be accessible. Here's what's truly exciting about future Europa missions. Engineers are designing nuclear-powered submarines that could melt through the ice shell and explore the alien ocean beneath. These robotic explorers would carry sophisticated instruments capable of detecting microscopic life forms and analyzing the chemistry of Europa's hidden sea. The discovery of life in Europa's ocean would prove that biology can thrive in environments completely different from Earth's surface conditions. Enceladus presents an even more accessible target for life detection because its geysers provide direct access to the subsurface ocean without drilling through kilometers of ice. Sample return missions could capture material from these plumes and bring it back to Earth for detailed analysis in the most sophisticated laboratories available. The organic compounds already detected in Enceladus's geysers suggest that this tiny moon possesses the chemical ingredients necessary for life. Titan, Saturn's largest moon, offers the possibility of studying an entirely different type of biochemistry. This world's thick atmosphere and lakes of liquid methane create conditions where life might evolve using hydrocarbons instead of water as a solvent. Future missions to Titan could include aerial vehicles that explore the moon's methane cycle and submarines that dive into its hydrocarbon seas. The outer solar system holds destinations that will challenge our engineering capabilities and expand our understanding of planetary science. Ice giant planets Uranus and Neptune have been visited only once, by Voyager 2 in the 1980s. Future missions to these distant worlds could reveal how magnetic fields form in ice-dominated environments, and why Neptune generates such powerful winds despite receiving minimal solar energy. Here's what makes exploration of the ice giants particularly intriguing. These planets may be the most common type of world in the galaxy. Recent exoplanet discoveries suggest that planets similar in size to Uranus and Neptune are more abundant than any other type. Yet we know less about ice giants than any other class of solar system objects. Breakthrough Starshot represents humanity's most ambitious exploration project, sending thousands of tiny spacecraft to Proxima Centauri at 20% the speed of light using powerful laser arrays. These postage stamp-sized probes would reach our nearest stellar neighbor in just 20 years, sending back humanity's first close-up images of an exoplanet. The technology required for breakthrough starshot pushes the boundaries of current engineering capabilities. Each probe must contain cameras, communication systems, and scientific instruments in a package weighing only a few grams. The laser propulsion system must focus enormous amounts of energy with incredible precision to accelerate these tiny spacecraft to relativistic speeds without destroying them. Here's what makes interstellar exploration so compelling. It represents the ultimate test of human ingenuity and our species' drive to explore the unknown. Even if the Proxima Centauri system contains no signs of life, the technology developed for this mission could eventually enable exploration of hundreds of nearby star systems, searching for worlds where life might have evolved independently from Earth. The development of fusion propulsion could revolutionize travel throughout the solar system, reducing journey times to the outer planets from decades to months. Fusion rockets could enable rapid transit between worlds, making the solar system as accessible as Earth's continents became after the development of jet aircraft. This technology would make possible ambitious projects like manned missions to the Kuiper Belt and detailed exploration of the thousands of moons that orbit the gas giant planets. Space elevators, if they can be built with advanced materials like carbon nanotubes, could reduce the cost of reaching orbit by orders of magnitude. These structures would extend from Earth's surface to beyond geostationary orbit, allowing cargo and passengers to reach space using electric motors rather than chemical rockets. Similar structures could be built on the Moon and Mars, creating a transportation network that spans the solar system. The universe has a surprise for us about how quickly these developments might occur. Technological progress in space exploration has historically exceeded even optimistic predictions. The first satellites led to lunar landings within 12 years. The first computers filled entire rooms, yet modern smartphones contain more processing power than the machines that guided Apollo spacecraft to the Moon. Artificial intelligence will play an increasingly important role in solar system exploration, enabling spacecraft to make autonomous decisions during long-duration missions where communication delays make real-time control impossible. AI systems could analyze scientific data in real time, identify interesting phenomena for detailed study, and even adapt mission plans based on unexpected discoveries. The colonization of the solar system will create new societies, with cultures adapted to life in low gravity, artificial atmospheres, and environments where a single equipment failure could mean death. These spaceborne humans may develop physical adaptations to their environments and social structures unlike anything that has existed on Earth. Here's what's remarkable about humanity's expansion into the solar system. We're not just exploring new worlds, but becoming a spacefaring civilization capable of surviving threats that could end life on Earth. Asteroid impacts, supervolcanic eruptions, or climate change could devastate our home planet, but a species distributed across multiple worlds would survive and continue to evolve. The economic opportunities of space development could dwarf any previous expansion in human history. The solar system contains virtually unlimited energy from the sun, raw materials from millions of asteroids, and real estate for billions of people in space habitats built from these resources. The first trillionaires may be those who successfully develop space-based industries and transportation systems, but perhaps the greatest adventure lies not in what we'll discover about other worlds, but in what we'll learn about ourselves. Living on other planets will force us to develop new technologies, social systems, and ways of thinking about our relationship with the natural environment. The challenges of space exploration will drive innovations that benefit life on Earth while expanding the horizons of human experience. The transformation of humanity into a spacefaring species represents not just a technological achievement, but an evolutionary step that will define our species for millennia to come. The children born on Mars will be the first humans whose native world is not Earth. They will grow up under alien skies, breathing artificial atmospheres, and thinking of the cosmos as their natural habitat rather than a hostile frontier. As we stand on the threshold of these adventures, we carry forward the legacy of all those who dreamed of reaching the stars. The same curiosity that drove ancient astronomers to track planetary motions now propels us toward becoming citizens of the cosmos. Tomorrow's greatest adventures will transform not just our understanding of the solar system, but our understanding of what it means to be human in an infinite universe. When you write your address, you might list your street, city, state, and country. But here's your complete cosmic address: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Observable Universe. That final line places you within a structure so vast that light from its edges has traveled for over 13 billion years to reach your eyes. Yet everything you can see, touch, or experience in your entire lifetime exists within just the first part of that address. Our solar system, a tiny island of warmth and activity in the cold emptiness of interstellar space. Our solar system serves as humanity's cosmic laboratory, a natural experiment in planetary formation and evolution that helps us understand the thousands of other planetary systems now being discovered throughout the galaxy. Here's what makes our cosmic neighborhood so scientifically valuable. Every world tells part of the story of how planets form, evolve, and sometimes die, providing crucial insights into the cosmic processes that create the conditions for life. The architecture of our solar system reveals the fundamental forces that shape planetary systems everywhere. The inner regions, dominated by small rocky worlds, show us what happens when planets form close to their stars, where temperatures are high enough to vaporize ice and drive away most gases. Mercury, Venus, Earth, and Mars each represent different outcomes of terrestrial planet evolution, from Mercury's stripped-down core to Venus's runaway greenhouse effect, to Earth's delicate balance that maintains liquid water. The outer solar system demonstrates how giant planets form and evolve in the cold regions beyond the frost line. Jupiter and Saturn, composed primarily of hydrogen and helium, show us how gas giants capture and retain massive atmospheres. Uranus and Neptune, the ice giants, reveal what happens when worlds form from mixtures of rock, ice, and gas in the frigid outer reaches of planetary systems. Here's what's remarkable about our solar system structure. It represents just one possible arrangement among countless variations. The discovery of thousands of exoplanets has revealed that planetary systems come in bewildering variety. Some contain hot Jupiters that orbit closer to their stars than Mercury orbits our Sun, while others feature planets in highly eccentric orbits that carry them from scorching heat to frozen darkness during each orbital cycle. Super-Earths, planets larger than Earth but smaller than Neptune, appear to be the most common type of world in the galaxy. Yet our solar system contains no examples of these mysterious objects. This absence may be crucial to understanding why life arose on Earth. Super-Earths might retain thick hydrogen atmospheres that create extreme greenhouse effects, or their higher gravity might prevent the development of complex life forms that require mobility. Earth occupies a privileged position in what astronomers call the habitable zone, ATI, the range of distances from a star where liquid water can exist on a planet's surface. But our world's ability to sustain life depends on countless other factors working in harmony. Earth's mass is large enough to retain an atmosphere, but small enough to avoid becoming a gas giant. Our planet's magnetic field, generated by its molten iron core, deflects harmful solar radiation that would otherwise strip away our atmosphere over geological time. The Moon plays a crucial role in Earth's habitability by stabilizing our planet's rotational axis, preventing dramatic climate changes that would make complex life difficult to sustain. Without the Moon's gravitational influence, Earth's axis would wobble chaotically over periods of millions of years, causing ice ages and greenhouse periods so extreme that multicellular life might never have evolved. Jupiter acts as our solar system's cosmic vacuum cleaner, using its immense gravity to capture or deflect comets and asteroids that might otherwise impact Earth with catastrophic consequences. Computer simulations suggest that without Jupiter's protective influence, Earth would experience major impacts roughly 1,000 times more frequently, making the evolution of complex life nearly impossible. Here's what the discovery of exoplanets reveals about the rarity of Earth-like worlds. Finding a planet in the habitable zone is just the beginning of the requirements for life. The planet must have the right mass, the right atmospheric composition, a protective magnetic field, orbital stability, and probably a large moon to stabilize its climate. It may also need a giant planet like Jupiter to shield it from impacts, and a star that remains stable for billions of years. Yet despite these stringent requirements, astronomers have discovered thousands of potentially habitable exoplanets, suggesting that Earth-like worlds may be more common than we once thought. The Kepler Space Telescope revealed that roughly 20% of Sun-like stars host Earth-sized planets in their habitable zones, implying billions of potentially life-bearing worlds in our galaxy alone. The chemical composition of our solar system tells the story of stellar evolution across cosmic time. The hydrogen and helium that dominate the gas giants are primordial elements created during the Big Bang 13.8 billion years ago. But the carbon, oxygen, silicon, and iron that make up the rocky planets were forged in the nuclear furnaces of massive stars that lived, died, and exploded as supernovas before our solar system formed. Here's what this means for our cosmic address. We are literally made of stardust. Every carbon atom in your body, every oxygen molecule you breathe, every calcium atom in your bones was created in the core of a dying star billions of years ago. The supernova explosions that scattered these elements across space also triggered the gravitational collapse that formed our solar system, making us the direct descendants of stellar death and rebirth. The solar system serves as our training ground for understanding astrobiology, AD, the search for life beyond Earth. The extreme environments we've discovered on other worlds expand our definition of habitability far beyond the narrow range of conditions that exist on Earth's surface. Life might thrive in the subsurface oceans of Europa and Enceladus, the hydrocarbon lakes of Titan, or the underground aquifers of Mars. These discoveries have profound implications for finding life around other stars. If life can exist in the dark oceans beneath Europa's ice, then potentially habitable worlds might orbit stars throughout the galaxy, not just those in the narrow habitable zones where surface water remains liquid. The number of potentially life-bearing worlds could be orders of magnitude larger than previous estimates suggested. Our solar system also demonstrates the importance of time in biological evolution. Life on Earth required nearly 4 billion years to evolve from simple bacteria to complex multicellular organisms capable of intelligence and technology. This implies that the search for technological civilizations should focus on planetary systems old enough for complex evolution to occur, probably at least several billion years old. The dynamics of our solar system reveal fundamental principles of celestial mechanics that operate throughout the universe. The same gravitational forces that keep Earth in a stable orbit around the Sun also control the motion of planets around distant stars. The tidal forces that create Europa's subsurface ocean operate wherever moons orbit massive planets. The atmospheric processes that drive weather on Jupiter and Saturn also shape the climates of gas giant exoplanets. Here's what makes our solar system invaluable for understanding planetary science. We can study these processes in detail, using sophisticated spacecraft and instruments, then apply what we learn to interpret observations of distant worlds that we can only observe as tiny points of light. Every measurement of atmospheric composition on Venus helps us understand exoplanet atmospheres. Every discovery about magnetic field generation on Earth contributes to our understanding of habitability around other stars. The solar system boundaries extend far beyond the orbit of Neptune into the realm of the Kuiper Belt and Oort cloud, where billions of comets preserve samples of the primordial materials from which planets formed. These icy time capsules carry organic compounds and water that may have been essential for the emergence of life on Earth. Similar comet populations probably exist around most stars, potentially delivering the ingredients for life to planets throughout the galaxy. The heliosphere, OMS, the bubble of charged particles created by the solar wind, defines the boundary between our solar system and interstellar space. This protective magnetic cocoon shields the inner planets from high-energy cosmic rays that could damage DNA and make life more difficult to sustain. The study of our heliosphere helps us understand how stellar winds from other stars might affect the habitability of their planets. As we stand on the threshold of becoming an interplanetary species, our solar system transforms from a collection of distant lights into humanity's next frontier. Each world represents a potential destination, each moon a possible home, and each discovery a step toward understanding our place in the vast cosmic community that surrounds us. The exploration of our solar system has revealed that we live in a universe far more dynamic and interconnected than our ancestors could have imagined. The same physical laws that govern motion on Earth also control the formation of planetary systems around distant stars. The same chemical processes that created life in Earth's oceans might operate in the subsurface seas of alien moons. The same impacts that delivered water to our planet probably occur throughout the galaxy, wherever rocky worlds form in the habitable zones of their stars. Here's what our cosmic address teaches us about our place in the universe. We are not separate from the cosmos, but integral parts of it. The atoms in our bodies were forged in stellar cores. The water in our cells may have arrived on comets from the outer solar system, and the oxygen we breathe was produced by billions of years of photosynthesis that transformed Earth's atmosphere. We exist because the universe has spent nearly 14 billion years creating the conditions necessary for our existence. The solar system also reminds us that we live in a universe capable of extraordinary creativity and beauty. The rings of Saturn, the great red spot of Jupiter, the polar hexagon of Saturn, and the geysers of Enceladus demonstrate that the same physical laws, which seem mundane in everyday life, can produce phenomena of breathtaking complexity and elegance when operating on planetary scales. Our exploration of the solar system has shown us that habitability extends far beyond the narrow conditions that exist on Earth's surface. Life might thrive in environments we once considered impossibly hostile: crushing depths of Europa's ocean, the methane lakes of Titan, or the underground rivers of Mars. These discoveries expand the possibilities for life throughout the universe and suggest that biology might be far more common and diverse than we ever imagined. The development of space technology has given us tools to study other worlds in unprecedented detail, revealing that each planet and moon has its own unique personality shaped by billions of years of evolution. This diversity teaches us that the universe is a place of endless experimentation, where the same basic ingredients, hydrogen, helium, and traces of heavier elements, can combine under different conditions to create worlds of stunning variety. As we prepare to spread human civilization throughout the solar system, we carry forward the legacy of 4 billion years of terrestrial evolution. The same curiosity that drove our ancestors to explore Earth's continents and oceans now propels us toward other worlds. The same ingenuity that allowed humans to survive ice ages and develop technology now enables us to design spacecraft that can function in the vacuum of space and the radiation fields of Jupiter. Our cosmic address places us within a universe that is both vast beyond comprehension and intimately connected to our daily existence. The sun that warms our faces began shining 4.5 billion years ago and will continue burning for another 5 billion years, providing the stable energy source that makes life possible. The moon that lights our nights was born from the most catastrophic impact our planet ever experienced, yet its presence makes Earth more hospitable for life. The solar system has taught us that we are part of something much larger than ourselves, a cosmic story that began with the Big Bang and continues through the formation of stars, planets, and ultimately, life itself. We are not observers of this cosmic drama, but participants in it, conscious beings capable of understanding our origins and contemplating our future among the stars. Here's the most remarkable thing about our cosmic address. It's not fixed. Humanity is preparing to expand beyond Earth, to establish permanent settlements on other worlds, and perhaps eventually to travel to other star systems. Our descendants may write their addresses as Mars, Alpha Centauri system, or worlds we haven't yet imagined, but they will carry with them the knowledge gained from exploring our solar system and the understanding that we are all citizens of the cosmos. The study of our solar system has shown us that we live in a universe where matter organizes itself into structures of incredible complexity and beauty, from the spiral arms of galaxies to the intricate rings of Saturn to the complex, a chemistry that creates life. We exist at a special moment in cosmic history when the universe has evolved conscious beings capable of understanding their place within it. Our cosmic address reminds us that we are simultaneously insignificant and precious, tiny specks in a vast universe, yet the only known examples of matter that has become aware of itself and capable of wonder. The solar system that seemed so strange and mysterious to ancient observers has become our cosmic home, a place where we belong not as conquerors, but as participants in the ongoing evolution of the universe itself. As we look toward the future, our solar system represents both our origin and our destiny. It's where we learn to be human, and it's where we'll learn to be something more, a spacefaring civilization capable of ensuring that the spark of consciousness that arose on Earth will continue to shine among the stars for billions of years to come. In the end, that may be the most important part of our cosmic address. We are the universe becoming aware of itself, and our exploration of the solar system is really the cosmos exploring itself through us.